So Newton's law of universal gravitation. Um, we're focusing in this video really on how to use it, really sort of the math side of it. In another video, I'll talk sort of about the more conceptual side of this equation, some of the consequences of some of the weird aspects of universal gravitation. But in here, we're really going to focus on using that equation, to calculate a force of gravity that two different masses, m1 and m2, which are separated by some distance r, and we're going to be able to calculate what the force is that they exert on each other, which we're still going to be labeling Fg like we have on free body diagrams in the past, so a force of gravity is what we're calculating. And the only other part of this equation that's not shown in this diagram is this constant, that capital letter G, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. You will notice, I'm sure, that this looks very, very similar to our equation for an electrostatic force, our Coulomb's law. That one, again, looked like this, K, some constant, times, not an M. We used to use charges here, then divided by an r squared. And basically what Coulomb's law let us do was, if we knew we had two charges separated, Q1 and Q2, and if we knew that distance that separated them, we could figure out the force that would act on them. And let's say that this, maybe this force was negative and this force was positive, then they would be attractive to each other and they would have the same electrostatic force pulling them each towards each other. Or if they were like charges and maybe we have two positives, then instead of having that attractive force, we would have a repulsive force and they would be pushing against each other. So we would have Q1 sort of push left and Q2 push to the right. But gravity is different, right? We have a force that is always attractive when we're looking at gravity. Masses are always attracted to each other. But functionally for us, the math side of using Newton's law of universal gravitation really is the exact same as how we used Coulomb's law before. We'll still go over three different types of problems. We'll talk about how to solve for this force of gravity, just like we solved for an electrostatic force. We'll go over how to solve for a distance between masses, just like we learned how to solve for a distance between two forces. And we'll learn how to solve for a missing mass, which is going to be exactly the same as how we solved for these missing charges before, right? So it's important to remember and draw on your previous knowledge, the practice that we've done before. That'll help you a lot within this video. So let's get to it. And before we start solving a problem, I want to make sure that I point out the units of each of these things, right? So our masses, the base unit for those masses is kilograms. So when we're sort of converting from like a word problem or some kind of description or real life situation to this equation or to the math side of this, when we start plugging in numbers, we want to make sure that our masses are in kilograms. And if you see kilograms, that's maybe a candidate to be plugged into one of these masses if that measurement in kilograms is one of the masses that we care about for that problem. And then for this r, that distance, that is still measured in meters. And our force of gravity is still measured in our Newton's capital letter N. That's not a great capital N. There we go. So anytime you see something maybe in a description or problem statement about something in newtons, that maybe is telling you what that force of gravity is. I don't want to say always, because I could give you 5 different numbers all in newtons and you might have to figure out which measurement in newtons should be plugged in there, but it's definitely a candidate if you see something in newtons. Okay, and let's put some numbers into this diagram here. So let's say that we know the mass of M1 is, let's say 3,000 kilograms. So M1 is going to be 3,000 3,000 kilograms. The mass of M2 is going to be 5.8 times 10 to the 9th kilograms, just to get some little scientific notation practice plugging into our calculator. And then let's say that our distance here, the distance between the two charges, is 5 meters. So the question for us is, what is the actual force of gravity that these two masses exert on each other? And they will be the same force that pull each of these masses into each other, even if they're affected very differently by the same force. We'll talk about that more later with Newton's third law, Newton's second law. So let's plug the stuff that we know into our equation. So we're trying to solve for what this Fg is, so I'll just leave that as our Fg. And we're always going to start out with that same constant, our capital G, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. And then let's start plugging in our masses. So I know mass 1 that we're worried about here is our 3,000 kilograms. Again, that mass is in kilograms, which can help us to solve these problems. And then our other mass here, also measured in kilograms. It doesn't matter the order that I plug these in, so I know a good question that people had asked when we were using Coulomb's law. Does it matter what you plug in for Q1, Q2, or M1, M2? Nope, as long as we plug in the correct masses for our M1s and M2s, it doesn't matter which we plug those in for, as long as we plug in our masses for those M's. So we're going to use our 5.8 times 10 to the 9th kilograms, all divided by our 5 meters squared. And I wanted to definitely include units in this video because I really basically ignored them in our last video. But you can sort of confirm as we check our work that our units are actually going to work out, so that our force ends up in the unit that we know it should end up in, and that's going to be newtons. So right now we have kilograms canceling out one of these kilograms in the denominator, and then the other kilograms canceling out the full sort of kilogram squared, right? We have kilograms squared in the denominator of this unit here, so that's getting canceled out by multiplying by kilograms times kilograms for each of these masses. And the other thing that is good for us as we sort of look at this, at the way that we've set this equation up, we have Newton meters squared, and then in our denominator we have 5 meters, and that whole thing is about to be squared. So our units here, our meters squared, is going to cancel out the meters squared in our constant. And so we will end up just with newtons, which is good for us. That's what we know that we should end up with if we're trying to calculate a force, and in this case, our force of gravity. So let's take a second to plug this into our calculator over here. So we've got 6.67 times 10, and then remember, the way that I like to do our scientific notation is I actually type out exactly what we see here, times 10, and then this little x to the y button to bring up our exponent, and then we can say to the negative 11th, and then I'm going to multiply by the next part, times 3,000 times, and then I'm going to put this in parentheses. You don't really need to, but it's a good habit. I'm kind of particular about how I do this, and you'll sort of figure out your own way to do this, but I like putting like anything in scientific notation or any like new value in parentheses. So 5.8 times 10, and then push our little x to the y to the 9th, and then I'm going to hit enter. So this gave us what the numerator basically of our equation is. And I'll just go ahead and plug that in, or excuse me, like record that, 1160.58. And the units on this top number, only the kilograms have been canceled out so far. I haven't actually, sort of divided by this meter squared yet. So right now that is still newtons meters squared divided by, and then we've got our 5 squared. You would know how to plug that in. I could just do 5 and then this little x to the y to the second power. But we know that our 5 squared is going to be 25, and the units for that are meters squared, since we took our 5 meters and then we squared that entire measurement. So our meters squared go away there. And then let's plug this into our calculator. So we have that 1160.58 Newton meter squared divided by 25 meters squared to give us just 46 point, we'll just round to 1 decimal because I'm running out of room, 46.4 newtons there. And so then the last step for us, as at least in future problems, will be to sort of then put this back on this diagram that we have, and if we were looking at one object, we would really focus on the free body diagrams there. But let's put 46.4 newtons on both objects. That's the strength of that gravitational pull that both of these objects are feeling as a result of their proximity to each other, right? So this 3,000 kilogram mass is exerting a 46.4 Newton force to the left on this much more massive object. And then this much more massive object is feeling that 46.4 Newton pull as a result of this 3,000 kilograms, right? So they're both being pulled towards each other as a result of their proximity to each other. Okay, so again, that's the simplest sort of kind of problem that we can solve with this big long equation. So the next kind of problem that we're going to try to solve is one where we solve for a missing mass. So let's say that we didn't know what one of these masses were, but we did know the other mass, and we knew the distance between them, and let's say that we knew the actual forces acting on them. So let's get our new numbers up here, and let's erase some of the stuff that we're not going to use here. Let's say that we have the same 3,000 kilogram mass. Let's say that our distance between these two masses is, let's choose something larger. Let's say it's 20 meters. Still pretty small in the scale or the scope of the universe. We don't know what this M2 is, that second mass. But we do now know what our force is. So let's say that these forces of gravity are each, let's say 300 newtons. No, let's say 400 newtons. So both of these masses feel that pull of 400 newtons on each other and towards each other, an attractive force as gravity always is. And we're trying to solve for this missing mass M2, or it could be M1, it's really whichever you prefer, but it's one of those missing masses, right? So let's plug in the stuff that we know. We know we have these forces measured in newtons, so let's plug that in first. 400 newtons, that's what we're plugging in for our FG, and that is equal to our constant that we always start off with, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And then we know what one of these masses is. We'll plug in for, or I'll plug in for M1 right now. So that's 3,000 kilograms. And then we don't know what that other mass M2 is. But we still do know our distance in the bottom, so I'm going to plug that 20 meters and make sure that I square that 20 meters. And again, the way that we can sort of figure out what information we have is by following those units. So something measured in meters, if I only have one measurement in meters and that's the distance between our masses, that's what I need to plug in for R, and I can use that unit as sort of a guide for what information we're actually being given there. So let's multiply the things together that we have first here, and let's just simplify this equation a little bit. So now that we've plugged everything in, let's take our 6.67 times 10 to the negative 11th times 3,000. Okay, and I'm just going to plug that part of this in. So we still have our 400 newtons is equal to 2.001 times 10 to the negative 7th times m2 all over, let's get our 20 squared. Some of you all might know that off the top of your head, but just since I didn't show this last time, I'll show it here. 20 squared is our 400 meters squared. So you might be wondering what the units are on what we multiplied together here. I should actually make room for that inclusion of the unit. So we multiplied a kilograms, and we still have a kilogram squared there, so it canceled out with one of those kilograms. So what we're left with here, Newton meters squared per kilogram. So basically one of those kilogram squareds, right, one of the kilograms was canceled out when we multiplied by our 3,000 kilograms. So let's see if we can solve for this M2. So there are a couple different ways that you could go about this. The way that I'm going to do this is basically to bring this 400 meters squared to the other side. So I wish I hadn't picked the numbers that I had here because it's going to be a little confusing, but I'm about to cancel out our 400 meters squared. And the way that I'm going to do that is by doing the opposite of whatever's happening with this 400 meters squared over here, right? So right now we are dividing our variable we're trying to solve for by 400m squared. So if I want to do the opposite of that, I need to multiply by on both sides by 400 meters squared. So that way, that goes away on the side where we're trying to solve for our M2. And what we'll be left with over on the right side, some of you all might also know how to do this off the top of your head. 400 times 400 is going to give us 160,000. And the units that we're left with here are going to be Newton meters squared, because we just multiplied something in the unit of newtons times something with meters squared. And we're just left with this on our right side, 2.001 times 10 to the negative 7th Newton meters squared per kilogram, all times m2. And so now we're really one step away. We just have one thing that's multiplied by our m2 now. And so right now, again, since that is being multiplied by our variable that we're trying to solve for, we need to do the opposite of multiply in order to cancel this out. So let's divide both sides by that 2.001 times 10 to the negative 7th Newton meters squared per kilogram. And so that's going to go away on our right side, right? That this 2.001 times 10 to the negative 7th divided by itself is just going to give us 1. So we're just going to be left with like 1 times m2 times that mass. And then on the left side, we can go ahead and plug this in. So we've got our 160,000 divided by, and then I'll put it in parentheses, 2.001 times 10 to the negative 7th. And what we are left with is a huge, ridiculous mass. Not actually ridiculous in the scale of things, but it's kind of silly for us to be looking at this compared to a 3,000 kilogram thing. And let's put this in scientific notation. You don't have to, it's okay in your work if you write out this whole long number, but it's it's convenient, and for anyone going into science in college, it's helpful to know and be really familiar with scientific notation. So scientific notation always has some number between 1 and 10. So let's go 7.9 and 7.99. So let's include a couple more decimals. Let's go 7.996. And then I'm just going to count how many times this decimal sort of had to move over in order to get to this 7.99. So it's going to be 7.996 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11th. 7.996 times 10 to the 11th. And then you might be wondering, what are our units going to be? Our Newton meters squared here are canceled out by our Newton meters squared there. And we have this kilograms in the denominator of something that we divided by. So we just get kilograms regular in our numerator, or sort of in our regular unit spot there at the end. If all this talk of units is stressing you out, then I would not worry about it terribly unless my future engineers, it's a very good idea to pay close attention to those units. Dimensional analysis is like broccoli for an engineer's brain. But for the rest of us who are not as interested in engineering, I would say it's important that we know how to recognize these units and know what our units should be in if we solved everything correctly, and then maybe make the assumption if all of the units that you plugged in initially up here, like we did, if all of those units were in our base units of newtons, kilograms, meters, then it's a fair assumption that whatever you were solving for, so since we were solving for mass, it's fair to assume that you also were going to end up in a base unit for whatever we were solving for here, that was kilograms. Right. So that is the second kind of problem that we can solve in this sort of large other equation for a gravitational force. Let's look at the third and final kind of problem. We've solved for a gravitational force. We've solved for an unknown mass. Now, what we're going to try to solve for is an unknown distance between two masses. Now, just like the other kinds of problems, that would mean that we have to know the other pieces of information in our equation. So that means that we must know both masses, and we also must know the force that those two masses exert upon each other. So let's put some values to that. Let's get all erased. Okay. Let's say in this situation, we'll keep our 3,000 kilogram mass. That's an old friend of ours now. And let's say that the other mass is 6.4 times 10 to the 10th kilograms. So another very large mass. And let's say instead of our 400 newtons, let's say that gravitational force that they exert upon each other is 1,500 newtons and 1,500 newtons. And that's an important concept, is that even though this object that I'm writing in blue is much more massive than our smaller one, they still exert the same magnitude force on each other. So it's not like this much more massive object exerts a larger force on the 3,000 kilogram object than it receives. Since they are the two interacting objects in this universe right now, they are exerting equal and opposite forces upon each other. And we'll talk a lot more about that when we get to Newton's third law later. Now the question for us, we want to know what our distance between those two charges is. So let's go ahead and solve this the same way that we have the other ones. Let's plug in the things that we know in this equation. So we have this measurement in newtons. That's the gravitational force that these two things exert upon each other. So let's plug that in to that part of our equation. 1,500 newtons equal to, and then we're always going to use that same constant. Let's zoom in a little bit. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Again, you do not really have to worry too much about the units throughout all of this problem solving, but it's a very good habit. It's a really good self-check. So if you feel comfortable doing that, I would definitely recommend doing that. It's a really helpful self-check, because if your units work out, there's like a 95% chance you've done what you're doing correctly. Let's plug in our other mass here. So we still have our friendly mass, our 3,000 kilogram mass, times the other mass now of 6.4 times 10 to the 10th kilograms. And then all of that is divided by some distance that we do not know. Let's use the same color as our distance there. So just like we have before, let's plug in some of these numbers that we know so far and just simplify a little bit. So what I'm going to do, I'm going to multiply sort of the numerator of our right side of this equation. So that would mean we're going to take our 6.67 times 10 to the negative 11th. Oh, I didn't hit this button correctly. To the negative 11th. And then times our 3,000 kilograms times 6.4 times 10, our exponent button, to the 10th. Okay, let's just write down what those three things gave us. So that leaves us still on the left side of this equation with 1,500 newtons is equal to 12,806.4 divided by r squared. For those of you who are interested in following these units along with me, our kilograms times kilograms, this is like a kilograms squared here because it's kilograms times kilograms, so that cancels out the kilograms squared in the denominator of our constant, leaving us with Newton meters squared. Okay, and now we're a couple steps away. So what we have here is our r squared, and we're trying to solve for r, that distance between our masses. That's stuck in the denominator right now. So let's first get that out of the denominator. So what we're going to do, let's multiply both sides by r squared, just like we have sort of in the past, but we've usually had a number there. But that's going to cancel out our r squared here, and that's going to leave us with 1,500 newtons. And I'm just going to put that in parentheses to keep my units, newtons, straight from our variable for that distance times r squared. And that's equal to 12,806.4 Newton meters squared. And we're still trying to solve for our r. So let's get rid of the number that's being multiplied by it. All right, let's get rid of whatever's next to it. And right now, again, we're multiplying by 1,500 newtons, so we have to do the opposite of that on both sides to get rid of it. Let's divide by 1,500 newtons. So let's see, that's going to cancel this out for us. And we'll just be left with r squared is equal to, and let's see what that gives us over here. So 12,806.4 divided by 1,500. And that leaves us with 8.5. Let's just round that to 4 to our second decimal place. And you might be wondering, for those of you following along with our units again, what are the units on this 8.54? Well, we have Newton meters squared over here, and then we've divided by our newtons. So our newtons go away here on our right side of the equation. Our newtons also canceled out over on the left side, but it was like this whole measurement, 1,500 newtons dividing by 1,500 newtons. So those both cancel each other out. And then on the right side, it's just the newtons really that cancel out. And then we're left with our 8.54. So this is now in meters squared. You might be noticing that we have our r squared, our distance squared, has units of meters squared, so that makes sense. That's a good sign for us. But if we want to know what our actual distance r is and not just our r squared, we need to take the square root of both sides. R is equal to, and let's come over here. Let's plug in our 8.54. You could keep the whole 8.5376. In fact, if I were taking a test or quiz on this, I probably would do that because I'm overly neurotic, but it's okay if you plug in just your 8.54. And we got 2.92 meters. And the way that we know that we would end up just in meters here is because we had meters squared, but we took the square root. So taking the square root of something squared is just going to give itself, right? It's like taking the square root of 5.5 squared would just give us 5.5. That's not a very clear example. But that's what that distance is between our two masses. So if we were to add that back up here, we could say that our distance is no longer a mystery. We have figured out exactly how far apart these two objects are, 2.92 meters. And again, if I think as a big takeaway, if you make sure that everything that you plugged in initially in this step right here, where we plug into this big sort of troublesome equation, if you know all of those units that you plugged in are in these base units of newtons, meters, kilograms, you don't necessarily have to give yourself headaches on what the final units for your answer are going to be. If you plugged in those base units, then you're going to get out a base unit for whatever you're solving for. So if you plugged in only kilograms and meters on this side of the equation, you're going to end up with newtons. And if you plugged in, let's say we were solving for a distance, if you only plugged in our kilograms, our masses in kilograms, and our force in newtons, then you're going to get your distance in meters. So you can trust those units as long as you plug in base units, but I wanted to make sure that I showed our units here because it's a good habit, especially for anyone who's interested in going into engineering. Dimensional analysis is very important and good for us.